In this video, I'm going to be talking about the shape and intensity of the peaks in an IR spectrum. The first thing that I'm going to be talking about is the intensity of the peak. The intensity of the peak is referring to how far down the y-axis a peak actually goes. So this peak right here would be a very intense peak or very strong peak because it goes all the way down, whereas these peaks here are not as strong or not as intense, especially this little guy right here, because they do not go very far down. The intensity or the strength of a peak is directly proportional to the strength of its dipole. The intensity of a peak is proportional to dipole of the bond. So a bond that has a very strong dipole is also going to have a very strong peak. For example, the oxygen-hydrogen bond. The oxygen-hydrogen bond has a very strong dipole. Big difference in electronegativity between the oxygen atom and the hydrogen atom. And that means that the oxygen-hydrogen peak is going to be a very strong peak in the IR spectrum. And in fact, this is the oxygen-hydrogen peak right here. So we can see that it is very strong. A bond that has no dipole would have no peak. And this is something that is easily forgotten when we're analyzing IR spectrum. So here would be an example of a molecule that has a bond that has no dipole at all. So due to the symmetry of this carbon-carbon triple bond, two methyl groups, one on each side, perfectly symmetrical bond, this bond has zero dipole moment. And because it has no dipole, that means that it does not have a peak. There is no visible peak in the infrared spectrum. If this particular molecule is 1-hexanol and it does not have a triple bond in it, but if this molecule did have a symmetrical carbon-carbon triple bond, we would not know, we would not be able to see a peak corresponding to that bond anywhere in the spectrum. It's hidden. This is not, I don't want you to think that this is just alkynes in general. If an alkyne is asymmetrical, so if we just go like this, all of a sudden now this triple bond is a polar bond and there is a dipole and there would be a peak for this triple bond. But when the triple bond is symmetrical, it just does not appear in the IR, and that's pretty tricky. So let's kind of label, let's say I want to label a couple of these. This would be an example of a strong peak because it comes nice and low down to the bottom, and this would be an example of a weaker peak because it does not come down very far. Now in terms of the shape of the peak, we have some peaks that are very spiky and we have some peaks that are broad and kind of rounded. Broad and also round peaks have two common causes. One cause, the most common cause, is the type of bond, OH bonds and NH bonds. These bonds tend to have broad and round peaks due to the hydrogen bonding interactions in the molecule. And as I had said before, this is the OH peak for this particular molecule, and so we can see that that OH peak is a real broad, rounded peak. Sometimes a broad, round peak is just due to poor resolution of the machine. Sometimes we run our machines at very low resolution because it makes the data collection process faster. Sometimes our machines are just kind of poor quality in general. When we have a low resolution machine, it does tend to give us more peaks that are broad and fewer peaks that are nice and sharp. And then sometimes the broadness or the roundness of a peak is just something that we don't explain very well, or we don't have an explanation for. So sometimes in chemistry, when we can see a sharp peak versus a broad peak, we just really don't know why. When we're looking at an infrared spectrum, we don't spend a lot of time thinking about why a peak might be broad versus why it might be sharp. And it's really not that important to us in terms of helping us analyze the molecule.